Hello everyone, my name is Salman and very recently I have started this online educational platform. Today we are going to discuss topic which is from mathematics and the name of the topic is mathematical induction. Mathematical induction is an inductive approach to prove certain statements, or you can say it's an indirect method to prove certain things. So, without wasting our time, let's get to understand mathematical induction. Now, the first question which person asks is what is mathematical induction? So, let me explain with a very cute example. A toddler is climbing stairs. In this snap, you can see that a very cute toddler is climbing the stairs. We make a statement that if he climbs nth step, he will definitely climb n plus 1th step. What does that mean? That means that if he climbs first step, this implies that he will climb 1 plus 1, 1th, that is second step. And if he climbs second step, that implies that he will climb 2 plus 1, means third, and so on and so forth. So by the above statement, his climbing of first step will mean that he will climb all the steps. I think this is clear. So this in a nutshell is all about mathematical induction. Now we have to see how we apply this. Now, as per the definition, mathematical induction is a technique which is used to prove a statement, formula, or a theorem for every natural number. This is very important. So this technique involves two steps. There are two steps here to prove a statement. First step, that is called the base step. It proves that a statement is true for initial value. That means the statement is true for initial value, say 1. So we initially do a check whether the given statement is true for n is equal to 1. That is the base step. So what is the second step? Second step is inductive step. That proves if the statement is true for a number n, it is also true for number n plus 1. So what do? We assume that it is true for n, and then we prove that if it is true for n, it is also true for n plus 1. So initially we assume that statement is true for n, where n is any positive integer, and we prove that result is true for n plus 1 also. If the above conditions are satisfied, means both the steps are okay. It is true for a base number, that is 1, and if it is true for n, it is also true for n plus 1. That means the statement Pn is true for all natural number. The same analogy which we had used when we had given an example of a toddler climbing the stairs, that if he climbs first, he'll climb 1 plus 1 that is 2, then 2 plus 1 that is 3, and so on and so forth. The first step, which is the base step, that is a factual statement, means you have already proved that it is true for n is equal to 1, say. So that is a fact. That's a factual statement. The second step is conditional one. If this happens, then this. This is a conditional step. So here, we first of all assume it is true for any positive integer n or k, and then we prove it is true for k plus 1. So second step is also known as inductive step, or we call it inductive hypothesis also, because hypothesis is something which we assume. So here we assume that it is true for n, and then we prove that it is true for n plus 1. We take one example. It is being asked to prove that 1 plus 3 plus 5 and so on plus 2n minus 1, this is equal to n squared. Now just see, in the expression on the left hand side, 2n minus 1 is the general term. First term is equal to, put the value of n as 1, 2 into 1 minus 1, which is equal to 2 minus 1 is 1. This is your first term. Second term, 2 into 2 minus 1, which is equal to 3. Second term, and so on. You can check it. Now, base system. We have to now check whether it is true for n is equal to 1. So put n is equal to 1. Then left hand side becomes 2 into 1 minus 1, that is 1. And there will be no other term. The right hand side is equal to 1 square, which again is equal to 1. So left hand side is equal to right hand side. That means statement is true for n is equal to 1. So your base step is over. Now comes second step, which is inductive step. And in inductive steps, first is inductive hypothesis. That means let the statement be true for n. That means 1 plus 3 plus 5 and so on plus 2n minus 1. This is equal to n squared. This is your first equation. Now you have to prove that that statement is true for n plus 1. So 1 plus 3 plus 5 plus 2n minus 1, and the next term will be, put n plus 1 in place of n, 2 n plus 1 minus 1. Now you have to prove that this is equal to n plus 1 whole square. Now consider this expression till this place. expression is n square. That means n square, our left hand side is n square plus 2n plus 2 minus 1, which is equal to n square plus 2n plus 1, which is equal to n plus 1 whole square, which is what you have to prove. That means the statement is true for n plus 1. We have already proved that it is true for 1, and proving that if it is true for n, it is also true for n plus 1. This implies that it is true for 1 plus 1, that is 2, 2 plus 1, that is 3, and so on. So it is true for all natural numbers. Now, we take one more example. Here it is being asked to prove that 1 square plus 2 square plus 3 square plus and so on plus n square. This is equal to n into n plus 1 into 2n plus 1 divided by 6. Now n square is the general term. So base step, put n is equal to 1. So this implies that left hand side will have only one term, that is 1 square. Right hand side will be put the value of n as 1, 1 into 1 plus 1 into 2 into 1 plus 1 divided by 6, which is equal to 2 into 3 divided by 6, which again is 1. So left hand side and right hand side both are equal. That means statement is true for n is equal to 1. Your base step is over. Now comes the second step, and in second step we have first inductive hypothesis. That means let the statement be true for n. Here the statement means this expression. Please don't get confused. Right, that means 1 square plus 2 square plus 3 square and so on plus n square. This is equal to n into n plus 1 into 2n plus 1 divided by 6. This we have assumed that it is correct. Now what do we prove now? Now want to prove that 1 square plus 2 square plus 3 square plus and so on plus n square plus n plus 1 square. This is equal to, put n plus 1 in place of n plus 1, and the second term will become n plus 2, and here it will become 2n plus 1 plus 1 whole divided by 6. That means this is equal to n plus 1, n plus 2 into 2n plus 3 divided by 6. Now consider this expression. Till this place we have already assumed that this is true. 1 square plus 2 square plus 3 square till n square, the value is this. So put it here. That means n into n plus 1 into 2n plus 1 divided by 6 plus n plus 1 whole square. This is equal to, you consider this as left hand side. Now take n plus 1 common and 6 as LCM. So what will be the remaining expression? N square plus n, and sorry, it will be 2n square plus n plus 6n plus 6, which is equal to n plus 1, 2n square plus 7n plus 6 whole divided by 6. Now just factorize it. N plus 1, this will be 2n square plus 4n plus 3n plus 6 divided by 6. So which comes to n plus 1 into n plus 2 into 2n plus 3 divided by 6. So this is what we were required to prove. Let's take one more example. Here we are being asked to prove by mathematical induction that 1 into 2 plus 2 into 3 plus 3 into 4 and so on till n into n plus 1. This equals to n into n plus 1 into n plus 2 divided by 3. Base step. But n is equal to 1. Left hand side will have only one term, 1 into 1 plus 1, which is equal to 1 into 2 is equal to 2. Right hand side, put n as 1, 1, 1 plus 1, 1 plus 2 divided by 3, which again is equal to 2. That means statement is true for n is equal to 1. Now, inductive hypothesis. Let statement be true for n. This implies that 1 into 2 plus 2 into 3 plus and so on plus n into n plus 1. This is equal to n into n plus 1 into n plus 2 whole divided by 3. This is the first equation, equation number 1. So we have assumed. Now we have to prove that this is true for n plus 1 also. That means to prove that 1 into 2 plus 2 into 3 plus and so on plus n into n plus 1, and the other term will be, you will have n plus 1 in place of n. That means n plus 1 into n plus 2. This we have to prove. This is equal to, now on the right hand side, instead of n, you will have n plus 1. N plus 1, n plus 2, n plus 3, whole divided by 3. Now left hand side is equal to, till this place we have already assumed this as value. That means now put it n into n plus 1, n plus 2 divided by 3 plus n plus 1 into n plus 2. N plus 1 into n plus 2 as common, n plus 1, n plus 2, and 3 as LCM. So the remaining is n plus 3. This is what we had to prove. That means the statement is also true for n plus 1. If it is true for n, it is true for n plus 1. Now since it is true for 1, it is true for 1 plus 1, that is 2, 2 plus 1, that is 3, 3 plus 1, that is 4, and so on and so forth. So it is true for all natural numbers. I hope the concept of mathematical induction is clear to you. Thanks for watching this video. Have a nice day.